Thank you, Amy. Hello, everyone. My name is Nagarajan Radhakrishnan. I'm a second-year PhD student here at Clarkson University. We're very pleased to host this month's lecture as a part of the monthly lecture series by AAR, and it's a pleasure to introduce Dr. Xingpeng Jiang, a professor from the School of Environment, Tsinghua University. He received his bachelor's and master's in environmental science and engineering from Tsinghua University. He received his PhD in energy, environmental, and chemical engineering from Washington University, St. Louis. Dr. Jiang's research involves topics in aerosol instrumentation, atmospheric new particle formation, and emissions from combustion activities. Today, Dr. Jiang would present about measuring size distributions of atmospheric aerosol using natural air ions. The lecture is in usual format where we take the questions the last. So I request all the participants to drop in the questions in the chat box, and we'll get to it at the end of the lecture. Thank you and welcome, Dr. Jiang.
Thank you, Nagar, for the nice introduction, and thank you, Amy. I'm very honored to be here to present some of the results. Actually, it's pretty early in China right now, and also I'm quite nervous. Even after all 3 years for the online meeting, I'm still trying to get used to look at the screen and can't see the audience. Anyhow, let's get started. So this talk is mainly about this paper actually published early last year, and I will report some of the results from here. And since it's already 1 year also, so in the talk I will also involve several new progresses on this topic. Given this audience, I don't think we need too much introduction. I will just have one few slides to briefly touch on it. Like in our community, we measure size distribution of atmospheric aerosols very often. One of the key instruments we use is electric mobility size spectrometer, for example, like SMPS or DMPS. The principle of this instrument, including 3 key components: the neutralization of the charging part, the classification, and the detection part. So typically, we bring atmospheric aerosol in and condition their charge state using generated bipolar environment. These aerosols can be radioactive material or soft X-rays. And after the charge, we assume that these aerosols were brought into a stationary charge state. For this state, a majority of particles are neutral. Some of them are positive charged and some are negative charged. Then we send them into a mobility classifier to select them based on their electrical mobility. So conventionally, we use either high positive voltage or negative voltage to select charged particle of one polarity. Then we send them into either condensation particle counter or aerosol electrometer. We can count these selected particles. So today, the talk on my focus will be on the charging part. However, I will also touch on the classification side, where, as I mentioned, right now, most studies, we only classify charged particle of one polarity. Later, we will discuss that if we classify both positive charged particle and negative charged particle, we may gain more information. So the motivation is that, like, if we zoom in to look at the neutralizer, like why actually a neutralizer is needed. So for the mobility classifier, we sometimes we also refer as a differential mobility analyzer. Only charged particles are selected and counted downstream. So what we got is actually a raw size distribution of either positive charge and negative charge. But what we really wanted is the aerosol size distribution as the inlet of the instrument. So that for this distribution, it includes both charged particle and neutral particle. So during the data inversion, the charge fractions were used in this process. So right now, for radioactive material-based neutralizer, a fixed charge fraction proposed by Dr. Ali Wieden-Solar was used in most systems. And for soft X-ray-based neutralizer, another fixed charge fractions was used and proposed by 2025. To be noticed that all these two sets of distribution are empirical fitting to charge fraction predicted by Fuchs series at a given ion property informations. So the key thing to mention here is that these charge fractions are fixed values. However, as we know, if we look at different conditions, so the charging fraction can vary. There have been many studies showing that the charge fraction are off from those fixed values. Here I give an example by a group leader by Dr. Ali Wieden-Solar, where they, when they do atmospheric measurement, they tested for both krypton-85 as the ionization source and also the soft X-ray as the source. So when the sources are new, they appear to agree with each other pretty well. What's plotted here is the typical size distribution they measured. However, as the soft X-ray become more aged, while it's not, the latter is not dead yet, so they can still do the measurement. They show that the soft X-ray, the aged soft X-ray achieved distribution are way off from the krypton-85 based neutralizer. So that's just one example showing during the real measurement, the charge fractions can change from those fixed values. And this is something pretty worrisome and need to be addressed. Another background is that if we look at the atmosphere, we have a bunch of both positive ions and negative ions, like generated by both cosmic ray and ionization processes. And the atmospheric aerosols are constantly conditioning by these ions. So one idea will be, okay, we are generating positive and negative ions during the measurement. Can we replace this neutralizer with the nature itself, where it's has both positive and negative ions and are similar to the neutralizer we typically use? So with these two questions, the first is, can we use the nature itself as a neutralizer to measure the atmospheric size distribution? So the second one is that the charge fraction are varying and can be different from the fixed value. So can we have some method to capture the variation in real time? So the solution or the method actually goes back to the theory, the principle we are measuring the aerosol. As I mentioned earlier, for the current mobility spectrometer, we often classify particle of a charged particle of one polarity. So what I'm showing here in a few recent papers is that if we classify charged particle of both polarity, and if we look at their relative abundance, their relative ratios, so this ratio actually reflects the computation between positive ions and negative ions. Because for this bipolar charging environment, where we have a computation among particles, positive ions and negative ions. So if the negative charged particle is higher than the positive charged particle for a given size, so that should indicate that the products of a negative ion concentration and their mobility should be higher than positive ion, the product of ion concentration and the mobility of a positive ion. So we showed that by looking at this relative ratio, we're able to retrieve an empirical parameter called ion mobility ratio. Basically, it includes both ion concentration and ion mobilities. And with this retrieval parameter, we can go back to retrieve the dynamic aerosol charge fraction. what I refer as dynamic in contrast to the fixed is that for any given raw cell distribution where you have positive charged particle and negative charged particle, we can retrieve ion mobility ratio and the corresponding charge fraction. So given that, we can combine this information, both the raw distribution and the dynamic charge fraction, and to obtain the aerosol cell distributions. For this previous study, we show both theoretically and in controlled laboratory environment that this new method can help to improve the accuracy of the data and also can retrieve the dynamic charge fractions. However, we haven't done it in real environment for a long time. So that's the question we have in mind. Therefore, at the beginning, we built a very simple system. We use a long DMA from TSI and also CPCs. While for the DMA, we use a dual polarity or bipolar high voltage supplier, where it can apply both positive voltage and negative high voltage to classify charged particle of both polarity. While at the beginning, the atmospheric aerosol can pass through a diffusion dryer. Here we can either use a neutralizer or without a neutralizer. We tested for different neutralizers for the case we use them. It includes both radioactive based neutralizer and the soft active neutralizer with different ages. Later I will show some result. In addition to the distribution measurement, we will also have some time we can bypass the DMA and to measure concentration by the CBC directly. Here is an example we run in Beijing since 2018. So the size range for the typical condition we set is around 10 nanometer to 700 nanometer. And we scan both, as mentioned, both positive voltage for 90 seconds and negative voltage for 90 seconds. The same after the scanning, we can measure the total concentration for 20 seconds by the CBC directly. For the atmospheric measurement, the typical resolution we have for 5 minutes, that's we often use for long-term measurement. This is the newest version of the instrument we are using here. So now we have like more than 4 years data. In the papers, we compare the measured data with typical SMPS where we have neutralizers. And we compare the integrated total particle number concentration with those measured by the CBC directly. We also compare the retrieved ion mobility ratios to look at its variations and compare with ion mobility ratios measured in other places as well. So here is some result. On the top panel is the size distribution measured using natural ions, that is to say without a conventional neutralizer. The bottom one is a conventional SMPS where we run a new soft active source as a neutralizer. We can see this natural ions, the system based on that can help to capture the general distributions of the atmospheric aerosols. Even in some time, we have a relatively intensive new particle formation events in Beijing. If we zoom in the data, we show the integrated number concentration between different size range. Here, for example, from 13 to 25, 25 to 100, and the larger ones. We compare these two systems and show that the data are pretty consistent with each other. And also, if we look at the geometrical mean diameter and the geometrical standard deviation, we showed that for the natural ions-based instrument, they are generally agrees with the conventional SMPS data very well. Now, if we look at the integrated number concentration versus concentration directly measured by the CPCs, what I plotted here is on these bars. The first one is using natural ions. We measure in this plot we show data for 150 days also, and the second one is krypton 85 source, and followed by soft active source with different ages for different time period. Generally, we can see the ratio between integrated particle number concentration from the site distribution agrees with those measured by the CBC directly. So for some are apart from each other, but generally they are within plus or minus 10% also with these ratios. Next is that we look at the changing of ion properties as time progresses. So the first one is for krypton 85. The one we have for this study is pretty old compared to its half-life time. The typical half-life time of krypton 85 is 10.8 years. So as time progresses, we see the retrieved ion mobility ratio. They actually show deviations as shown here from 0.76 and fluctuate to these values. And also to notice that to develop these fixed charging fractions, the ratio used for these radioactive material-based charge neutralizers is 0.875. And for the neutralizer we test here, they are often the time is away from the value used to derive the fixed charge fraction. So this data shown is for the soft X-rays, and this middle one, the green data, is a new soft X-ray, which we see its ion mobility ratio is somewhat below 1, and when it's aged, it can actually go up slightly, sometimes above 1. While in comparison, that's this red dashed line is the ion mobility ratio we use to people use to develop the fixed charge fractions, 1.957. So for ions, that's shown in the black dots here. We see over the time, generally it is quite stable. However, for any given time period, it fluctuates a lot, but generally this is pretty consistent with each other. So we also compared the retrieved ion mobility ratios with many other studies where they use different instruments to measure the ion mobility ratio directly. We can see this retrieved data in urban Beijing are generally fall in the same categories with other instruments. So that's the result for that specific paper I mentioned earlier. And after that, we built 6 small set of instruments, and we deployed in both Beijing at Peking University, and Shanghai, Wuhan, Shenzhen, and Zhuhai, and Kunming, in different places in China. They have a relatively different environment. Some are in the urban, some are in the suburban environment. But we're trying to see whether at different variety sites, these natural ions are both the methodology of natural ions are working very well. And by doing this measurement, we are actually collaborating with different colleagues to doing this measurement. At Peking University, we work together with Professor Mei Zheng, and Shanghai, Dr. Chen Huang, at Wuhan, Dr. Xiaoxiao Li, and in Shenzhen, Dr. Hao Wu, and Sun Yat-sen University with Professor Jun Zhao. Kunming is with Professor Ning in Kunming. So as I'm showing here is daily average particle size distribution measured at each site. Generally, we are pretty happy to see this methodology works in different environments at different sites as well. So we also compare the integrated number concentration from the site distributions with that direct measure with CBCs. The data show pretty well, pretty good agreement as well. And this slide shows the derived retrieved ion mobility ratio for these 6 different sites. Generally, the ratio are close to 1 and during this period. we start this network of measurement from early April this year, and the measurement is continuing going on. We can also take this data to calculate, for example, the new particle formation frequencies at different environment and the growth rate for a given size range. This is just showing an example, and it's not the key of these specific talks here. So another thing I would like to mention, so by removing these charges and using natural ions, we can actually have a tendencies to make the electrometer, to make the mobility spectrometer smaller and more compact, and also improve its accuracy as well. So we shown an example. If we take a TSI nanoscan SMPS for this specific study, it's model 3910, and we replace its unipolar charge. We remove that unipolar charge and use natural ions, and we change the polarity of the high voltage so that we can measure both charged particle and negative charged particle. We tested its accuracy compared to a reference SMPS, and also clearly by doing so, we will reduce the size. And if we do the long-term measurement, the maintenance will also be reduced. So we show that for both before the modification and after the modification for this system compared to a reference SMPS, as shown on the red plots. In the top is the original one without modification, where we show number concentration comparisons and the geometric mean diameter and geometric standard deviation of distribution. So clearly, we show, so after the modification, we can improve the instrument at the same time make it smaller. So another example was taken from the International Aerosol Conference last year. This was done by Dr. Susan Herring and Professor Rick Flecken's group, where they work on the spider DMA and magic CPC, trying to make it more portable. What they shown here is for the dual polarity measurement. This specific plot is with the neutralizer. I remember during the talk, Dr. Amanatides also showed result without neutralizer and show pretty good consistent. So to summarize, we showed in the study that the atmosphere itself is a natural neutralizer and can be used for measuring aerosol size distributions. And we show the dynamic charge fraction in contrast to the fixed charge fraction we often use by the bipolar SMPS, help to improve the accuracy, and it can reflect the real-time variation in ion properties. And this helps to reduce the uncertainty which has been troubles people a lot when we think about the long-term atmospheric environment. For example, like when the neutralizer will die, when the soft X-ray will become not working. So early example shows that even when the soft X-ray is still working, the distribution can deviate from the presumed distributions. And also we show that by removing this neutralizer, it improves both the feasibilities of the long-term atmospheric environment and also provide opportunity for developing miniature spectrometers for applications such as airborne measurement, exposure studies, and sensor network. So with that, thank you for your attention. So the results are presented here mainly by Ms. Ian Lee and several other students in collaborations. I'll be happy to take questions. Thank you.
So thank you so much for the talk, Professor. And now request the participants to type in the question. You can go ahead and ask.
Can I ask a question?
Yes, Michelle, please.
Hi, Jin Kun.
Good to see you, Michelle.
It's 2 a.m. in Paris. No. In fact, I'm in America.
You're in America.
Yes,
at Yale then. Yeah.
Yes. Thanks for your talk. You didn't told me that you have tried the small radial DMA. What's the name? Is it the nanoscan?
Yeah.
Nanoscan instrument, and it uses radial DMA. So my question is not about this instrument. The question is about the particles which are smaller than 10 nanometers. Do you think that you can extend the method to the sub 10 nanometers? Is there any reason that it will be different in the sub 10 nanometers?
It's a very good question.
Now you are using the long TSI DMA. In case you have used the short TSI DMA, do you think that you will have the same results?
Yes, Michelle, this is a very good question. So there are some reasons we start with the particles above 10 nanometer. So one reason that even though these same principles should work with particles like sub 5 nanometer as well. However, when we develop this algorithm to retrieve ion mobility ratio and to retrieve dynamic charge, aerosol charge fractions, there are some assumptions we use to make the equations simpler. And this simplification process, as reported by the two papers, cannot be directly used for sub 5 nanometer. To do so, we need to modify them somewhat, and we are working on it. So that's the plan. And when this pilot work is done, that's the plan to go further to even smaller particles.
Okay.
We don't have the result yet, Michelle, but that's the plan because, as I mentioned, the principles should be similar.
Okay. Thank you.
Thank you. Yeah.
And congratulations for the nanoscan, because it was really a good idea to use it.
I dropped an email to Brian yesterday as I prepared the talk. See why the TSI are interested.
We have a couple of questions in the chat box. I see Rick Lagan has raised their hand. You can.
Yeah. Jin Kung, fantastic talk. Really enjoyed it.
Thank you.
I have a question for you that you may have evidence for in your data. If not, I would be interested in your speculations. There are events where ion-mediated nucleation is important in the atmosphere, which means that as the nuclei are originally formed, they're charged. There are also cases where particles in the very low nanometer size range are emitted charged from many high temperature sources, combustion sources. That will happen. When you are looking at such a system, have you seen any evidence of transient biases that may decay with time as the charges approach that ultimate steady state charge distribution? Or if not, what do you think will happen? How long would you have to wait?
Thank you, Rick. This is a very good question. We tested it. Like at the beginning, we have this concern very much so, especially for example, like for the atmospheric environment in Beijing, we often have intensive new particle formation. So we are concerned during the intensive new particle formation, we have a bunch of new particles, whether they can really be a stationary state. That's one thing we tested. And we also move the system in Beijing close to a highway. It's when I say close, it's not. It's still like around 400 meter also. We do see strong emissions from the vehicles. So similar argument will be for the ion ion nucleation. However, at the ground surface, let's say in Beijing and in the sites we tested in other places, at the ground surface, they are not that important versus the other pathways. But if we do move in a higher altitude, I believe ion-induced nucleation will be stronger. So given that said, I don't think that actually changing this methodology, because as I arguing in this talk, we don't need it to be a stable distribution, like what we hoped for previous like neutralizers. So its charge diffraction can be varied. All we needed, I believe, is the computation process between positive ion and negative ion with the particles. If they are have certain time to be reflected by the retrieving process. So that is to say, if I show the ions in the ambient for the air ions, we see their ratios are actually changing dynamically. So that gives some confidence that even in that case, together with the event measured in Beijing, where we have a strong new particle formation and also emission from vehicles, so the distribution works pretty well. So we compare that with the neutralizer using a new software grid, and the result looks pretty convincing to me. Rick, did I answer your question?
Well, you've addressed the question. I think there are still questions there. One is that when you have strong nucleation, the number of gas ions in the atmosphere is limited. And so if you have very strong nucleation, that nucleation may overwhelm any, you may overwhelm the possibility of ion-mediated nucleation and may not have that bias. That bias I would expect to be much stronger in weak nucleation events where the ions could dominate.
Yeah, I see your point. So another thing, like what Michelle was asking, for these studies, we addressed the particle above 10 nanometer also. So I remember what Dr. Kanjiro Ida done back in Minnesota when he was doing his PhD studies. So the ion-induced nucleation, their influence of the charge diffraction started with a very small particle. So when they grew big, so they gradually were neutralized by the ions. So I would expect if we go further, smaller, as what Michelle asked during the first question. So we may see further what you discussed here. That's the case, like in Beijing. The new particle formation rate are much higher than typical weak environment. However, in the ongoing study I'm showing here, like in Kunming and in Zhuhai, several other places here, so their new particle formation events are relatively weak compared to Beijing or Wuhan's. We can dig in more on these events to see it. But on the other hand, like I mentioned, most likely they will have a more influence on smaller particle, like nanometer size range.
It might also be interesting at those cleaner sites to look at the primary emission charged particle possibilities, because again, you may be able to distinguish them better if there's not a huge background.
Yes, sure. I agree with you on it. Thank you. Yeah.
Again, thank you for a very nice seminar.
Thank you, Rick. Thank you for being.
So there are quite, like I said, quite questions in the chat box. A question from Yang Wang: have there been measurements of the chemical composition of these ions?
Hi, Dr. Jiang. Just wanted to say hi. It has been a long time, and
Hi, yeah.
thank you for
Good
the
to
great
see you.
talk. Yeah. Yeah, so my question is about the measurement of these ions. So have there been like any measurements or guess of the chemical composition, also regarding the number concentration of these ions? Because I would think that this charging process, because it's diffusion charging, then it's going to take some time, right? Because if the ion concentration is relatively low, then the charging will take a pretty long time to reach the steady state. So have there been some measurements on that? And if we think of an extreme, so if we generate some neutral particles and introduce them into the air, how long will them reach to this steady state charging state under the natural ions?
Thank you. Yeah, yeah, very good question. So in Beijing, we have 2 papers published on the ion composition. I can forward to you later. We use an epitoph, it's a time flight mass spectrometer, to measure its composition. We see a bunch of the ions, and some are related. I mean, when doing that measurement, we were not thinking the charging. Actually, we were thinking new particle formation. But then we realized that data can be used to understand this neutralization and charging process as well. So we do have this information. But for these other sites, we don't have it yet. So that's the plan. Maybe we will select a few of them to do some additional measurement on that. The other question was on the
concentration of these ions.
Concentration and the time scale to reach that. So
yes.
The thing is that the more we work on the charging process, the more we, like conventionally, we have this parameter called NT, like the ion concentration time, the resonance time. However, the more we look at this system, you will realize the ion concentration is changing, especially the relative abundance of positive ion and negative ion. In a typical condition, the negative ions are smaller than positive ions, so they will lost quickly. So that should imply the distribution is changing, no matter how long is your concentration time, the resonance time. We did that back in Minnesota while I was doing postdoc for downstream most typical neutralizer. If you do smaller tilting to tweak it, you will see the distribution actually shifting. So that's the true motivation for all these years to driving us to continue work on the charging and eventually to develop this so-called dynamic charging fractions. So the key thing, I believe the key thing is behind this plot that, so as addressed here, it's this charging is competitions between these bipolar ions and the particles. And we know the ions are changing dynamically. So as a result of that, I don't believe we have a fixed stationary charge distribution for given typical system. So that's why we should go to this. If we really want to make this fraction right, we should have the idea that there is no so-called fixed stationary charge distribution, even you wait long enough for that process to happen, because the ion is changing. I'm not sure I make this point clear enough. Yeah.
Yeah, thank you.
Thank you, yeah.
We have a question from Chanakya. How feasible is this method for indoor environments?
Yes, we were starting with the ambient environment, and for this specific TSI nanoscan study, we also tested in indoor experiment. For the experiment we done, it shows it works pretty well. for this question, and I encourage you to look at this specific paper. If you have questions, can contact me on this. We can share the data as well. Yeah. So, but certainly more measurement needs to be done. For this, our study, we focus more on the ambient atmospheric measurement.
Okay. We have another question from Diego. In one of your slides, you highlight different conditions that impact the concentration of natural air ions. Does relative humidity in the surrounding air impact the concentration of natural air ions, and would that in turn affect the SMPS measurements?
This is a very good question. So if we believe this black dot showing the retrieved ion mobility ratio is true, so that actually reflects what this question is asking. So these ions are dynamically varying. So that's what also goes back to Professor Yang Wang's question. So what we really experience in the ambient, the ions are dynamically changing. And also, I truly believe inside the neutralizer we typically use, the ion concentration and the ion distribution are also changing with responding to the inlet aerosols. So as I tried to explain, the beauty of this methodology is that, okay, the ions can change. So we are happy that it's changing. What we do is we look at the positive charged particles and negative charged particles. So their relative abundance always reflects the changing of the ions here. So think about that collision process. It's much quicker than what we are discussing here.
Thank you. We have another question from Jiao Liang. Does this method perform multiple charge correction?
Yes, Xiaoliang, thank you for the question. Good to see you. We did. So once we have an ion mobility ratio, we showed that in the paper that we can retrieve both fractions of our single charge and double charge and more particles with moles. And in the inversions, we utilize both positive charge particle and negative charge particle, and also including these multiple charge corrections. Yes.